if there are any questions about the discussion we had in the last two talks. If you have any questions, please go ahead. I can try and address them. Yesterday we looked at a pair of quivers. Which is derived from the same brane system. And the pair we took was the simplest possible one. So these fonts are large enough? Oh, I need to make it bigger? Okay. Okay. Bigger. So oh, the pressure puts pressure into the game. So let's do that. And 1 and n. This is the first quiver. Let me remind you the brane system. So 2 Neve-Schwarz 5 branes. There is a single D3 brane. And a collection of n D5 branes. This is the system, and so you could see that the number of 3 branes is the rank of the gauge node. We get 3D n equals 4 SQED. And the other quiver is looking like a set of n-1 nodes. And one flavor on each side. It's the same brane system, and in this brane system, this quiver looks like coming from those n D5 branes and n-1 D3 branes, which are stretched between them. And there's one more here. And one more here. Any question about the derivation of the quivers or the derivation of the brane system? Kimion, good to see you. Okay. Okay. And so we can now discuss the formations, so the parameters. Of the gauge theory. For this particular theory, we have one Phi-Heliopoulos term. And I have n masses. Now, also I remind that this brane system is drawn in the 6, 3, 4, 5 directions, and this brane system, the same brane system, is drawn in the 6, 7, 8, 9 directions. Okay? And so we have to be careful when we count the number of masses. We see that in the 3, 4, 5 directions, I have n positions of the D5 brane and 1 position of the 3 brane. Altogether, I have n plus 1 parameters. There is an overall parameter which doesn't play a role. We are only measuring distances in this system. So this overall parameter is scaled away. So actually, when I count the masses, I should change this to n minus 1 masses. Is this point clear? Okay. So because I have the freedom to choose the origin of coordinates, and because I measure distances, I have one less mass parameter. How do I see the Fayet-Leopold term? I go to this picture. Well, let me also say that these are positions of D5 branes in the 3, 4, 5 directions. On the other hand, here, I have the position of the 2 Neve-Schwarz 5 branes in 7, 8, 9. So the Fi term is the position in S5. So there is a natural symmetry. If I exchange the D5 and the Neve-Schwarz 5 brane, I exchange masses by Fayet-Leopold terms, and this exchange is naturally coming in type 2b as S duality. So D3 brane becomes D3 brane, Neve-Schwarz 5 brane gets exchanged with the D5 brane. Okay? Now let's again look at the picture that we have over here. I have n minus 1 positions of 3 branes. Those will be considered as moduli, vacuum expectation values of scalar fields. So each position is going to be a vacuum expectation value. And there are positions of the heavier branes, the D5 branes, the Neve-Schwarz 5 branes, which are, because they are heavy, they are going to correspond to parameters in the Lagrangian, not to vacuum expectation values. Right? So let me put here that the 3 brane positions are vacuum expectation values of scalar fields, whereas D5 and Neve-Schwarz 5 are parameters they set the gauge theory. They are masses, they are Fayet-Leopold terms. Once I fix them, I can study the corresponding quantum field theory. Any questions about this point? Fayet-Leopold term. So in this picture, I have 2 positions of 5 branes and n minus 1 positions of 3 branes. And so so as we argued here, those n-1 positions will parameterize the Higgs branch. Right? Remember from yesterday, the Coulomb branch of this theory, so we will call it the Coulomb branch of the 1n theory, is C2 mod Zn, and the Higgs branch is the closure of the minimal nilpotent orbit of SLN. So that's the Higgs branch. Let me erase the Higgs branch of the same quiver is the closure of the minimal SLN orbit. Now, you're asking how do we see the Fayoliopoulos terms? So we see that there are two positions of the Navier-Schwarz 5 branes, and as before, I still have the freedom to set the scale, not the scale, to set the origin in 7, 8, 9 directions, right? So out of those n-1 moduli, which is the dimension of this space, and the dimension of this space is 1, these will be the moduli, the vacuum expectation values, and these are going to be the parameters of the theory. So they are going to be fixed. And so I have one distance. Out of two positions, I can have one distance. One of them I set to be at the origin. Okay? So this is the distance here. So if I put them over here, the Fayoliopoulos term will be 0. But otherwise, it will be non-zero. And they are the deformation parameters. So in geometry, the Fayoliopoulos term is the deformation parameter of the moduli space of the minimal SLN orbit. Whereas the masses are the deformation parameters of the moduli space of C2 mod Zn. So a bit of geometry here. The way we should think about this moduli space is as, well, first of all, let's identify the global symmetries. So the global symmetries are SUN for the first case. Let's call it M1, and let's call this one M2. For M1, and U1 for M2. How do we see this global symmetry? So the global symmetry is actually identified with a gauge symmetry on the 5 branes. So let us go back to this picture. In this picture, I have n D5 branes, which can be coincident. When they are coincident, I'm going to get a UN gauge symmetry living on the world volume. Out of this UN, only SUN will interact with the fields on the brane, on the 3 brane, and that's why I get this SUN global symmetry. On the other hand, if I look at this picture, I have two Navier-Schwarz 5 branes, but they are far apart. So there is a U1 gauge symmetry here and another U1 gauge symmetry here. And because of this choice of center of mass, because for the case of n masses, I drop from n to n minus 1. Here I drop from UN to SUN. And over here, I have U1 times U1, but there is an overall U1 that I can remove. So this is a symmetry on the Navier-Schwarz 5 brane. And this is the gauge symmetry on D5. Any question about this point? Does it address your concern about the Fayet-Leopold term? Why the Fayet-Leopold term shows up in supersymmetric theories? So whenever I have U1, so in general, for every U1 gauge symmetry, there is one Fayet-Leopold term which transforms as a triplet of the R symmetry which acts on the Higgs punch which is in this case SU2. We will denote it by SU2H just to tell us that there is an SU2. And actually, we can go back to the brane picture and look at this case. So the Fayet-Leopold term, the position of the Navier-Schwarz 5 brane is a 3 vector in 789. And so we identify the SU2H as the rotation group in 789. Okay, so I guess I was assuming this, and I wrote it here explicitly. So if you look at the supersymmetric action, each time you have a U1 gauge field, you could turn on a Fayet-Leopold term. It's a very important piece of the physics of any supersymmetric gauge theory. So I would recommend that if it's the first time that you've seen Fayet-Leopold term, then just try and look at the literature about it. Well, what does it mean to break supersymmetry? Here is a situation where I turn on the Fayet-Leopold term. It is a distance between the Navier-Schwarz 5 brane, but nevertheless, the supersymmetry is not broken, right? I mean, all of those branes are drawn in such a way, they stretch along orthogonal lines, right? They stretch along all of those directions of the 3 branes, the 5 branes. It's a consistent configuration. It doesn't break supersymmetry. There are ways to, if you have enough matter fields, there are ways to turn on a Fayet-Lapalus term and to keep the supersymmetry. One way we can interpret what you're saying is that since the Fayet-Lapalus term is a parameter and it does transform under SU2R, when I turn a vector in 3 space, I pick a direction and I only have a residual symmetry, which is the rotation around this vector. So in this sense, you could interpret it that this is a breaking, but it's not a real breaking because I can form it into this particular brane system, and it still will be consistent with supersymmetry. It breaks the R symmetry. You could, some people argue that by picking a direction along the R symmetry direction, you're breaking supersymmetry, but it's not really the case. From the point of view of the brane system, it's more like a spontaneous breaking of the rotation symmetry. It's not worse or better than just taking a set of vectors in 3 space and picking and arguing that, have I broken rotation symmetry? Yes or no? So under rotation, they will move to another direction. So it's just the physics of playing with vectors in 3 space. And that's one of the nice things about the brane systems, that it really gives us an intuition about the physics of the supersymmetric gauge theory. So the Fayet-Lapalus term may look like an exotic object, but by the end of the day, it's just a 3 vector in 3 space, right? So everything you know and want to say about vectors in 3 space applies here. More questions? So it looks like quite a system. I have an SUN symmetry which acts on the space which is the minimal SLN orbit. Let me remind you, we had an explicit computation of it. In terms of matrices, it's the set of n by n matrices which has 0 trace squared to 0 and rank at most 1. And so there is, because there is an n by n matrix here, there is natural SLN action. On the other hand, C2 mod Zn is just the set of 3 parameters x, y, and z, such that xy is equal to z squared, z to the n. And there is a natural symmetry here. There is a U1 symmetry if I take x to lambda x and y to lambda minus 1 y and z to itself. that's a natural symmetry. So this is the U1 symmetry. So this is related to the statements that we were saying before, that there is an SUN global symmetry for the first space, and there is a U1 global symmetry for the second space. Any questions about that? Now here, the next point is a conceptual point, that for every global symmetry, we have fields in background vector multiplets. Well, I should be more precise, not just vector multiplets, super multiplets. So we need to be precise about this point. What are those background supermultiplets? So if I look at this picture, we just said that there is a UN gauge symmetry on the world volume of the D5 brane. These are gauge fields, scalars, and fermions, which live in 5+1 dimensions. To an observer on the 3 brane, all of those fields will look like background fields. So I couple them in the action in the same way I couple background fields. They don't have kinetic terms. They only have the couplings to, if it's a gauge field, it's a coupling to a current. If it's a scalar field, it's a coupling to some of the fields on the 3 brane, which we said are either the masses or the Filopoulos terms. And if these are fermions, those are fermion sources for other fermions. So for every global symmetry, we have fields in background supermultiplets, and so we will be explicit here. So, so for the U1, I'm going to have a background hypermultiplet, and for SUN global symmetry, I'm going to have a background vector multiplet. But this is in the picture of a U1 with n flavors. It's in the first quiver. But on the other hand, if I write the other quiver, those roles will get exchanged. So the hypermultiplet will become the vector multiplet, and the vector multiplet will become the hypermultiplet in the picture of the other quiver, 1. Is this point clear? Right? We are exchanging Coulomb branch by Higgs branch. We are exchanging masses by Filopoulos term. And so whenever I have a pair of quivers, the roles, the mass here is going to be the Filopoulos term here, and the mass here is going to be the Filopoulos term over here. Right? That's a very important point to realize. Any questions about that? This is conceptual. I mean, you must have questions about this. So. So it's you see, yes, just by symmetry. I have two. So here I specified the R symmetry which acts on the Higgs branch. There's also an R symmetry which acts on the Coulomb branch. And I will call it SU2C. What is this SU2C? It's the rotation group in 3, 4, and 5 directions. You see, there is a rotation group in 3, 4, 5, and there is another rotation group in 7, 8, 9. Here, the positions of the Neve-Schwarz 5 branes are transforming as vector in 7, 8, 9, and over here, the positions of the 5 brane are transforming as vectors in 3, 4, 5. Of course, yes. I'm just making the point that I'm not going to write any Lagrangian. I'm just going to look at the brane system and get the interpretation. It makes life harder in this way, but I think one needs to make the transition. You could just make all of these statements by just looking at the brane system and the different gauge symmetries which arise on the different branes. Okay, so let's go back to the piece of geometry we were saying. This space has a natural global symmetry SUN. So I called it here SLN action, but in the more physics terms, there is a natural SUN which acts on those variables. Whereas in this case, there is a natural U1 which acts on the variables. And so, because I have a background supermultiplet, either a hypermultiplet or a vector multiplet, I'm going to, the next thing that I'm going to do is to say that for each gauge field, so if I look at the gauge field on the D5 branes, I have an SUN symmetry. There are scalars transforming in the vector multiplet of the gauge fields, the SUN gauge theory, in 5 dimensions. They transform in the adjoint representation, right? So on the whole volume of the D5, I have one gauge field or an SUN gauge field, and I have scalars in the adjoint representation of SUN. I could also diagonalize them by putting eigenvalues, M1, M2, all the way up to Mn, with a condition that I can just set that sum is equal to 0. That's the condition. This is the choice of center of mass that I'm picking in 3, 4, and 5 directions. And so what is the interpretation of this the eigenvalues of the adjoint SUN matrix, those are nothing but the positions of the D5 branes. Okay? Now, what do they mean geometrically for this space? So if I look at this space has n-1 deformation parameters and there is a simple way of seeing this by saying that I take this equation, xy equals z to the n, and I deform it to a generic polynomial. Now, here I need to be careful. This is a complex variable, x, y, and z. M are triplets, so what I'm going to do is to pick 2 out of 3 scalars in Mi. So Mi is a 3 vector. What I'm going to do is to pick 2 of them, complexify, leave the third real one, and not use it in the equation. So what I did by this, I said that this singularity now becomes non-singular. It's a geometric space. It's still one-dimensional, but geometrically what happens is that there are n-1 two spheres in C2 mod Zn, and the masses, and the volumes of those S2 are given by some function of the MIs. So now the space, instead of being a singular space, instead of being a conical space where there is a singularity and all the other points are in a cone, I just resolve the singularity by I have n-1 different parameters to do this deformation given by those masses. Okay? But look at the beauty of this point. Those deformation parameters of this space are actually in the background vector multiplet of this space. So there is a correspondence between those two spaces. Right? I have an SUN global symmetry. There are scalars which are superpartners of this, of the gauge fields, the global symmetry, and those scalars are the deformation parameters of this space. Okay? This is the phenomenon that the mathematicians are calling symplectic duality. And so I'll say it in words. The superpartners of the global symmetry on one space are the deformation parameters of the other space. Right? I have two moduli spaces. If I fix a quiver, I'll have a Coulomb branch and a Higgs branch. So the Coulomb branch has a global symmetry on it. Because it has a global symmetry, I should find scalar fields. Those scalar fields will be the deformation parameters on the Higgs branch. Right? So I fix a quiver, and I make this statement. I can do it in both ways. I can take the second quiver that we had there and pick, either look at the Coulomb branch or the Higgs branch, look at the isometry, look for the scalars, and those will be the scalars that deform the other geometry. Okay? It's a very beautiful connection between those two spaces, the Higgs branch and the Coulomb branch. Any questions? Very good. So that's a very important question, right? So remember that I'm dealing here with D5 branes, right? What is the world volume theory of the D5 brane? It has a gauge field, but it is a supersymmetric theory. So there are scalar superpartners, right? There are 4 scalars that the D5 brane has. One scalar which tells me the position of the D6, of the 5 brane along 6, and this turns out to be not relevant for the field theory, and therefore I ignored it. I didn't talk about it. And there are the 3 scalars, which are the positions along 3, 4, 5. Those scalars are the superpartners on the gauge theory that lives on the D5 brane. So here's the power of supersymmetry. I have heavy branes. They come in supermultiplets. They have 16 supercharges, right? So the theory on the D5 brane has 16 supercharges. The theory on the Weschwarz 5 brane has 16 supercharges. So there is a gauge field over here, and there are 4 scalars. And there is a gauge field over here, and 4 scalars. U1 times U1. And overall U1 decouples, so I'm left with the difference of the scalars, right? So whenever I have a global symmetry in quantum field theory, if it is supersymmetric, I should also look for scalars because they have to form supermultiplets. And those scalars have a crucial role in the physics of the problem. So this is actually, here we are using one of the first steps in understanding brain physics. This goes back to the statement of taking parallel D-branes. When they are separated, they each has a position, and those positions are the eigenvalues of a joint valued matrices, right? I'm sorry. Suppose that I have take randomly the P brane, then I have 9 minus P scalars, which transform in that joint representation in case I have n of them. Since it's in the joint representation, I take an n by n matrix, and because of the supersymmetry, I'm also allowed to diagonalize it. And the eigenvalues are those which get the physical interpretation as the positions of the branes. So that's what I did. I just used the one of the first steps that we do in understanding dynamics of branes. More questions? So why do they call it symplectic? So the physics translation of the notion of symplectic is, for us, it just means that it has, it's supersymmetric with 8 supercharges, right? So if we go back, let's start with the quiver here. This quiver has vector multiplets and it has hypermultiplets. There are scalars in vector multiplets and there are scalars in hypermultiplets. And they each can admit vacuum expectation values. Because of the amount of supersymmetry, the moduli space of vector multiplets is hyperkähler, and the moduli space of hypermultiplets is also hyperkähler. Okay? Now, in the mathematics literature, the word hyperkähler, if in addition the space is singular, gets translated to symplectic. There is a symplectic form, and there is also a holomorphic structure. So, so in the mathematics literature, these two spaces are called symplectic holomorphic. Because I use complex numbers, and in addition, there is a symplectic form which I didn't have, so far I didn't use, but it's certainly there. So symplectic here for us means supersymmetric with the right amount of supersymmetry. So if you don't like the name symplectic duality, call it the correspondence between Failliopoulos terms and mass terms, right? The Failliopoulos terms are making the moduli space smooth, but in addition, they transform in background supermultiplets, which is the isometry of the other space. Okay? So once you think about it, it's a very beautiful duality, and there are many games you could play. So let's see something that I suppose most of you didn't see before. Well, this space has now a prediction. How many deformation parameters does this space have? Well, I can just look at the quiver. The isometry of this space is U1. So I should find a single scalar field, a triplet. We call it the Failliopoulos term. That's the position of the Neve-Schwarz 5 branes. And so I would expect that this space would have one deformation parameter. Indeed, the resolution, so here's another mathematical term, it's called symplectic resolution. Named after Springer. So if you are interested, you could look at the literature for Springer resolutions. And mathematicians are taking singular spaces and they ask, does there exist a resolution which keeps the supersymmetry? Which brings us back to the question of this Failliopoulos term. And so we just argued that this particular space has one parameter, one triplet, which resolves this space. And so the resolution of the closure of the minimal orbit of SLN is given by a cotangent bundle over a projective plane or projective space. And the mathematical notation for this is T star. That's the cotangent bundle over P, the projective space of dimension n-1. And we have the nice interpretation that this deformation parameter is just the size of this Pn-1. Is the size okay? So we didn't really need to know. I mean, you could also take those equations and look for deformation. From this equation, it is clear that trace of m squared is equal to 0, but once I deform, it becomes equal to some parameter. Let's call it eta. Yes, that's right. That's right. If I take the quiver here and I turn on the Filopoulos term, it will deform the moduli space of 1 SUN instanton. Very good. So you see how the brain system gives us quite a nice bit of information about the geometry. It also gives some things about the algebraic structure, but I didn't go over it. Any questions? Excellent question. Very good. Ask your question.
Yeah, so many of the formulas you wrote are written in formalistic way, so you chose one complex structure.
Very good.
Yeah, for example, eta, the parameter eta which appeared in the equation you just wrote down
Is complex.
complex. And the parameters that appeared in the resolution or deformation of the C2 to C8 are also complex.
Very good.
So then you wrote P star of Pn minus 1. And that resolution, does it correspond to deformation by a complex parameter, like complex parameter eta, or does it correspond to resolution by the remaining real parameters?
Yeah, so a hyperkähler singularity has 3 complex structures which transform as a triplet of the R symmetry. So it's either SU2C when I talk about the Coulomb branch, or SU2H when I talk about the Higgs branch. And when we do this notion of symplectic and holomorphic, we keep the symplectic form, but we pick 1 out of 3 complex structures. So think about being in 3 space. I just pick a direction. I pick a direction. There is the transverse direction, which I can complexify, and I'm staying with the direction that I picked. So we pick one complex structure, and your choice is as good as any. And with respect to this complex structure, now I have a notion of a holomorphic function. Let's do a simple example. The simplest hyperkähler space is C2. It's the simplest space. Hyperkähler singularities always have dimension divisible by 4. So I'm just picking the simplest possible space, and it's also flat, C2. So let's try to understand. Any idea that you want to test, do it on the simplest possible space. So C2 has 4 coordinates, x1, x2, x3, and x4. What does it mean to pick a complex structure? I can take x1 and x2 and I can complexify them. And then I'll complexify the other 2. But I can also pick x1 and x3 and do the other 2. And I can have many options to complexify. So I just pick one. Once I declare what is a holomorphic function, I can work with just the holomorphic function. But what does it do to my deformation parameters? I have 3 of them. Let's call them M1, M2, and M3. I pick 2 of them, M1 plus I, M2, to be complex. Then I'm left with a 3rd one. Now, the reason you're asking your question is because you are mostly used to work with Calabi-Yau singularities. There is a Kähler space over there, not hyperkähler. So I don't have a triplet of complex structures. And therefore, I don't have this distinction. I have just one notion of holomorphic function, and I can give sense to a deformation and resolution. So once I pick this choice, this I call, well, that's in the mathematical literature, this is called deformation, and this is called resolution. But because of the amount of supersymmetry, I can always rotate those m's among each other. It's just a choice that I'm making. So the notion of deformation or resolution for hyperkähler singularities doesn't mean much, right? I can always rotate one to another. So it's very important that you ask this question, and that we will clarify that because of the amount of supersymmetry, we are able to rotate between resolutions and deformations. That's right. So M here is complex. I forgot about the real one, and I can ask, okay, can I do, instead of a deformation, can I do some resolution? And I'll say one comment. I didn't plan to talk about it. The resolutions can be given by a set of background magnetic charges or baryonic charges. Which is another beautiful piece of the story that allows me to understand deformations and resolutions through the physics of this problem. I did not introduce magnetic charges, and then I did not introduce the baryonic charges, and therefore it's hard to talk about it. So I'll just leave it as a comment. More questions? In the Lagrangian, yes, it's just, you write the three-dimensional theory. Let's say we talk about masses. Every quark field has its own mass, and the mass is a triplet, that because of the supersymmetry. So to proceed, I will now pick a complex structure. So I'll pick 2 out of 3. I refuse to call it in this way. It's not correct. I pick a complex structure. It's not a choice of a subalgebra. It's not. It's just sometimes it may happen that the choice of supercharges that you're making in order to complexify form a subalgebra, but it's not necessary. In 5 dimensions, there are 8 supercharges. In order to pick a complex structure, I just need 2 out of 8 supercharges. Those 2, together with their conjugates, will not form a subalgebra because I'm in 5 dimensions. But it doesn't stop me from picking a complex structure. The complex structure is inherent to the structure that I have of hyperkähler. Once I have a hyperkähler, I am able to pick a complex structure. It says nothing about the ability to pick a subalgebra or not. So we really need to make this distinction. It is actually a common mistake that people are making. Sometimes you could form a subalgebra, but it's not necessary. You're not using it. If you check in all of the cases where it was claimed that you're picking a subalgebra, you're not using the property of having a subalgebra. So you don't have to insist that it's a choice of a subalgebra. More questions? Yes, yes. I haven't looked at this type of twisting, but you just apply the usual twisting procedures, and If you are in 3 dimensions, you could. In 5 dimensions, you won't be able. You'll do twisting, but not subalgebra. So there is a recent work. I just heard a talk. Alberto Zaffaroni was visiting us in London, and he gave a talk about his index computation after performing a twist in 5 dimensions. So I'm not so familiar with the details, but certainly, so his team checked all of the computations and came up with very nice sets of results about twistings. And they do it in 3, in 4, in 5. I think he left it as a challenge to move to 6 dimensions. So certainly you can. More questions? Okay, so this, the stuff that we talked about goes under the name of 3-dimensional mirror symmetry. I don't like the name mirror symmetry. We're not really doing a mirror. I think we should not use the word mirror or duality too many times. We should use different names. It's a nice phenomenon. It's a map between 2 quivers. And there are historical reasons why the name mirror symmetry was chosen, but I think that it is not particularly justified. So this 3D mirror symmetry says that the Coulomb branch of quiver 1 is the Higgs branch of quiver 2, and vice versa. Okay? Which is different from symplectic duality. We should emphasize it's not the case of symplectic duality. Symplectic duality talks about the deformation parameters. It says that the isometry of 1 has natural scalars attached to it, and those will be deformations of the other space. Right? So I fix a quiver. I don't pick a pair of quivers. I fix a quiver, and I say in symplectic duality that the isometry of the Higgs branch will be the deformation of the Coulomb branch, and vice versa. Okay, so it's important to make the distinction between 3D mirror symmetry and symplectic duality. So in fact, the original way the mathematicians came up with the notion of symplectic duality was to take a pair of quivers and to say the Higgs branch of 1 is related to the Higgs branch of the other. Right? They didn't know about Coulomb branches. So they just talked about Higgs branches. Now that mathematicians understand the notion of a Coulomb branch, they just say, okay, I pick a single quiver, and the isometry parameters of one space become the resolution parameters of the other, right? So the notion, once you introduce a Coulomb branch as a mathematical term, you could just pick a quiver and talk about its both moduli spaces. But on the other hand, 3D mirror symmetry really makes a claim that Coulomb branch of 1 is Higgs branch of the other, right? So we should really make this distinction. You just showed the reason why I don't like the notion of mirror symmetry. This is very different. What you were talking about now is mirrored symmetry between compact Calabi-House. There's no hyperkähler structure, and the moduli spaces are compact. Here, we are talking about hyperkähler spaces, and they are singular with deformation parameters. It's completely different. The geometry is very different. And so there's no reason to call the two phenomena mirror symmetry. That's right. In compact Calabi-House, you map deformation parameters of one theory to Kähler moduli of the... For which? For 3D mirror symmetry or for mirror symmetry of color? There's nothing here about supergravity, so I'm not sure how to relate this, right? Because it's not clear. We are certainly not gauging any of the R symmetries, not SU2 on the Coulomb branch, and not SU2 on the Higgs branch. So here, I suspect that CMAP is yet again a different phenomenon. Maybe it's related, but we are here talking about very explicit, gauge theory, Coulomb branch of one, Higgs branch of another. So we really have to check it and make sure that when we give names to phenomena, first of all, don't give names because they resemble something else and give the same name, because then people get confused. If people hear about it for the first time, they say, they must be related. But the logic that led one to say why this should be called with the same name is not necessarily the same logic that you are using after you understand enough. Also the word duality. The word duality is used so many times for so many occasions. It's a complete abuse of a single word. Just, you have different phenomena, call each one with a different name. That's my personal view. Right. Okay. Okay. So what would you like to call it? 3D duality. Then it will be an abuse. Correct. Yes. So, and by saying duality, what you really mean is take a UV theory, flow to the infrared, and check what kind of fixed point you end up with, right? And this whole sentence is summarized in a single word, duality, right? Infrared duality, okay. Anyhow. More questions? Mm-hmm.
Then you started with a different quiver, and you also showed how to compute Higgs branch.
Very good. So
you in both cases you arrived to some moduli spaces, and then you announced that the second Higgs branch is actually a Coulomb branch. The first.
Absolutely right. I did not explain how to construct Coulomb branches. I probably avoided it. So let me say some few words about Coulomb branches. So Coulomb branch is the space of dressed monopole operators and I need to explain what I mean by this, right? So the reason we were able to derive the Higgs branch in a relatively simple way is because it's a classical moduli space. I just take the Lagrangian and I compute the solution to the vacuum equations. But the Coulomb branch receives quantum corrections. And so I need to have a way to control these quantum corrections. How do I treat them? There is another point that if I look, we will now concentrate on this theory with U1 and N flavors. So we will make an attempt to compute the Coulomb branch for this theory. One immediate thing we can observe is that there is a gauge field, U1 gauge field. It has a field strength, F, and this field strength satisfies the Bianchi identity, which I can rewrite D star J equals 0, where J is star of F. F is a 2 form, J is a 1 form. So this is a conserved current. And it's topological. Because its current conservation follows from the structure of space-time, from the geometry, and not from the details of the equations of motion. Which tells us that the Coulomb branch now is characterized is divided into sectors with fixed magnetic charge. Which is the charge under this current. Now, since this current is just an abelian current, we have magnetic charge, which is an integer magnetic charge. Right? So when we think about the Coulomb branch, we really need to think about infinitely many sectors, each sector characterized by magnetic charge. Okay? Very good. I have states and I have operators. There is a state operator correspondence. I have a, so as Sergio was saying, we are flowing in the infrared. We hit a conformal field theory, and this conformal field theory has a collection of operators which satisfy some OPE, and there is also a state operator correspondence. You could do that, yes. And so let's try to argue for existence of such. So, for example, if I take the gauge field, and again I have the field strength, and I rewrite the field strength as a derivative of a scalar field. That's the process of duality. We were talking about duality yesterday. So I take what am I doing here? Star. And so I just rewrite the field strength as a derivative of some scalar field. And so F is a 2 form, star brings it to a 1 form, and sigma is a 0 form. It's a compact scalar. And so now what I can do is to construct states of the form e to the I sigma. And if I act on them with J, then I'll get a magnetic charge. So if I'll take, this is a purely classical statement. I just take this into a Poisson bracket and act with a current. If I'll multiply it by m, then I'll get that the state Vm, which goes like e to the I sigma m, has magnetic charge m. So certainly we have such operators in the spectrum. However, we are dealing with a supersymmetric theory, and therefore we better complexify. Sigma is a real scalar, and so what I can do next is to add it, vector multiplet has 1 gauge field and 3 scalars. So what I'm going to do is making this choice of a holomorphic structure. I'm going to separate the 3 into 2 and 1. The 1 will complexify the dual of the gauge field, and I'll be left with the remaining 2. Right? So I'll have sigma plus I phi 3, and I'll have phi 1 plus I phi 2. So here's a choice of a complex structure. If you don't like this choice, pick another one and you'll get the same results, because we are free to pick any complex structure we wish. Any questions? Yes, you have a Lagrangian, there is a natural Poisson bracket, classical. Yeah.
So to compute the Poisson bracket, you use the Lagrangian that contains sigma?
Yes, you could. Yeah, after dualization, right? Because this will become the momentum. This will be the momentum of sigma, and when you act with the momentum, you'll just differentiate. Right? It's a completely standard exercise. Not even canonical quantization. You don't even need this. Right? Just classical physics. More questions? Well, it's just for convenience. So you see, in the talk of Francesco, we saw the quaternions, and maybe it's possible to reformulate everything that we are doing here in terms of quaternions. But it turns out that by picking a complex structure, you get quite some nice things. If it will be possible to generalize to quaternions, this will be even nicer. I just don't know how to do that. It's much easier to do it with the complex numbers. Right? So it's just, we just use it. I want to understand a complicated space. We call that the minimal orbit of SLM. What ways do I have in order to understand it? Okay, so I'll pick a complex structure and see what kind of holomorphic coordinates I have. What kind of ring do they form? Right? I'll just test it. If I can get far, then that's very nice. If I get stuck, maybe I should use a different way, right? Because I want to understand both the geometry of this space and also to extract the relevant physics of this problem. And this resolved in case I turn on mass parameters of Aeliopoulos terms, right? Or I could leave them to be zero. That's a perfectly acceptable physical system, and then I have to deal with singular spaces, right? So it's both are relevant to the physics. I'm not asking here questions of mathematics. Mathematicians take a singularities and they ask whether it's possible to resolve or not. It's not my problem. My problem here is to understand physics and to use geometry as a tool in order to extract the relevant physics and algebra. Okay? So we learn of the existence of Vm, and in the quantum theory, they will not be just these simple operators. There will be complicated operators. Maybe semi-classically they will look like this, but I'm not going to be concerned about the precise way they are. I just postulate the existence of such operators of fixed magnetic charge M, and because of supersymmetry, I'm going to also assume that they are BPS. So the energy, which is typically denoted in the literature as delta M, proportional to the magnetic charge. Here's the computation. I'll just specify the result. So this energy naturally is proportional to the number of flavors. So it has a contribution of n. Each flavor contributes with the same amount. So this is reasonable. The energy is also proportional to the magnetic charge. So the more distance I get from the sector with zero magnetic charge, I'll have a linear growth. And this 1/2 here is the basic unit of the representation of SU2. Because of the supersymmetry, I have that delta is a highest weight of SU2R, and the representations of SU2R come quantized in units of 1/2. So that's the reason for this 1/2. Now we don't have much time, so I'll just tell you the final picture. So here's that graph of delta. I'll do it like this. Right, so M is the horizontal direction. Here's the charge 0, charge 1, 2, 3. And I picked for the special case where N is equal to 4, I believe. Yeah. Okay. The next thing I'll do is to have dressing factors. And I don't have much left. The only thing I'm left with is the collection of scalar fields, phi1 plus phi2, which I will just call simply phi. Now phi is complex. So I just have powers of phi, because phi does not carry a magnetic charge. Phi to the k. So I can have one phi here, another here, another here. Those are the different powers of phi. And if I start from this monopole operator, I could have one phi here, here, here. And so I get a lattice of operators. Okay? It's a very nice structure. These are all the operators in the chiral ring. And they form a cone. They form a nice cone. If I collect all of these guys as the space of functions or the space of operators in this theory, it turns out that this is precisely enough. We don't have more, we don't have less. And so here's the construction of the Coulomb branch. I took monopole operators, I put dressing factors. And since our time is over, I'll just finish by this. There's plenty of more things to say, but we don't have the time for that. Thank you.